of stoichiometry. So stoichiometry of gases, I feel like we are pretty good with this, hopefully, because we did this in 209. And so we should be pretty comfortable with this. So we're going to talk about reactions involving gases. And when we're doing this, we're going to usually use the ideal gas law, but we might use our little magical conversion, 22.4 liters. That's always a great one. Okay, so when you're doing a gas law problem, how do you know if you need to do stoichiometry? There's always kind of a serious hint, and that hint is there is a balanced chemical equation. If you see that balanced chemical equation, that means a mole-mole ratio is about to happen, right? 99.9% of the time, that is your hint. This is a stoichiometry question. And so in a stoichiometry question, there's always a mole-mole ratio somewhere it's going to happen. So in this case, it says what volume of H2, so we want liters of this, is needed to make 30.75 grams of, there it is, mole ratio, right? They're talking about two different things. So we're starting here and going here. So somewhere in this calculation, I'm going to have this mole ratio. So I hurt my hand. So my writing is going to be worse than normal. I apologize. I might be a little slow today. Over 2 moles of hydrogen, or vice versa, right? Somewhere we're going to be using this mole ratio, right? It could either be written as is or flipped over, but it's going to happen somewhere. Okay, so it says what volume is needed to make 35.7 grams of CH3OH at 738 mmHg and 355 Kelvin. Okay, so where do we start here? So here's what we're given. So we are given information about the CH3OH, but they're asking for hydrogen, right? So we want to go from one to the other. Okay, so that means we need to do a mole ratio. Okay, well, 37.5 grams of CH3OH, can we go from grams of this and then get over here? Totally, we can literally go grams, molar mass, hydrogen. Easy peasy, right? That's just straight stoichiometry. We can go from grams of here and we can get to moles of hydrogen. So when we're doing gas stoichiometry problems, just like our other problems I talked about, they're kind of never the same. So you can't just go, I do this, then I do this, and this goes on the bottom and I multiply. Nope, that will never work with a gas stoichiometry problem because we can ask them in like 50 different ways. So again, don't memorize them. Use this right here. This is always your roadmap. So they're giving us grams of this. We know we want H2 because that's what it asks for. So we need to get from grams of that to hydrogen. And we know how to do that just doing stoichiometry, right? So just quick stoichiometry, 37.5 grams of CH3OH. I mean, I don't even know what the molar mass is, but grams of CH3OH in 1 mole of CH3OH. And now we can do our mole ratio, right? So this one's going to go on the bottom so we can cancel it out. And then moles goes on the top, right? So we've been doing this forever, right? And I mean, I'll look at this molar mass later. So when we do this, we're going to end up with moles of H2. So do you see how what I did in the problem is I didn't go, oh my gosh, how am I going to do this problem? No, let's get to the part I know I need to get to, right? A lot of times the problems, if they get overwhelming to you, just take one piece, then do the next piece, then the next piece. I know they're asking me for hydrogen. So I know the only way I can go from something to something else is a mole ratio. So I did that. And now I have moles of hydrogen. Now I know this is the gas law chapter. And remember in the gas law chapter, EV equals nRT is our best friend. Okay, so now we have moles of hydrogen. We always have R. We have temperature. We have pressure. We need volume. Easy peasy. Now it's just a PV equals nRT problem. So when you're doing gas stoichiometry problems, there's usually like a little stoichiometry and then a PV equals nRT, or PV equals nRT, little stoichiometry, and then another PV equals nRT. So it again changes, but it's usually like something you're familiar with, like stoichiometry. And so here's the exact thing I just set up. There's my molar mass. And then you're going to use PV equals nRT. So it's a combination. So you're going to use your PV equals nRT or our little magic 22.4 liters. But again, that doesn't count here because we're not at STP. And then you use PV equals nRT. So here was that molar mass that I hadn't added up here. So now I have my moles of my hydrogen. And so now I can use PV equals nRT. There's a lot of little details to keep track of here. That is in millimeters of mercury. It needs to go to atmospheres, right? I feel like we're professionals at doing this since we've now done it a few times in lecture and lab and in your homework. So we get our pressure, 0.97 atmospheres, and then we just plug that into PV equals nRT, right? And so we're going to use this equation, volume equals N times R over P. Our moles of hydrogen is here. Our atmospheres, our pressure is here. Our temperature is already in Kelvin, so we don't need to do anything. And we have R. Remember, you don't need to memorize these units because this is always given for you. Whenever you use R, you have to use these units. But again, you don't need to memorize it because this is given. You just look at the units and you go, oh, I need atmosphere, liters, moles, Ks. All right, so when we plug all of that in, which I'm not going to write it because my hand is crazy. So there's our moles of hydrogen, our R, our temperature, our pressure, and we get 66.9 liters. And all of our units indeed cross off. Okay, so again, when we're doing stoichiometry of gases, it's always like a mixture of stoichiometry and a PV equals nRT, or maybe sometimes two PV equals nRT. But somewhere there's a mole ratio happening, right? So it's kind of just mixing what we were doing with a mole ratio. Nothing of it is new, right? PV equals nRT is not new. Mole ratios are not new. We're just putting the two of them together. So there's no new concepts happening here at all. We're just putting them together now. All right, let's look at this one. How many grams of water will form when 1.24 liters of hydrogen reacts completely with oxygen? Okay, so what do I see here? First of all, I see a balanced chemical equation. So I'm probably doing a mole ratio. So we want grams of water. And again, this is our roadmap. So we want grams of this, and they're giving us 1.24 liters of this. And what does this mean? Reacts completely with oxygen? Nothing. Oops, sorry. Thank you. Not grams of water. Grams, I can see the difference between water and hydrogen and grams of water. So they're asking for water, but giving us hydrogen. So we're going to have to go from one to another. So somewhere I'm using this. Where? I don't know, but it's going to happen. Or we write it the other way, 2 moles of water. Oh, this really hurts my hand. 2 moles of hydrogen. You get it, that's a mole ratio. Somewhere this is happening, right? Because I've got to go from one to another. What does this mean, reacts completely with oxygen? It just means like, no, it doesn't matter. Oops, the STP does matter, right? So what is the STP? Again, that's telling us our temperature is 273 Kelvin and our pressure is 1 atmosphere. We just need to memorize that. That's just like short for not having to say all those things. But it does say STP here, doesn't it? So STP, so we don't have to use this fun, awesome conversion unit, but remember at STP, that does not look like a P, 1 mole of any gas equals 22.4 liters. So that's just another stoichiometry, 1 mole, 22.4 liters, or 22.4 liters over 1 mole, right? It's just something I can use. I don't have to use it, but it makes my life easier if we do, because it's faster. You can do it using the ideal gas. Absolutely, you can, but you don't have to. So let me just erase this so I can put this piece. So here's what we have. We have the mass. So, and we want to go to grams. So we have to go from one to the other. So a mole ratio is going to happen. We're starting with liters of hydrogen. Now we could use, so if we do PV equals nRT, look, we have volume, right? Volume of hydrogen, right? We have temperature, we have pressure, and we have R. So we could get to moles of hydrogen, and then we could do our mole ratio. And then we would have to go to grams. And so then we could go to grams. Not so bad, right? So we could use PV equals nRT. Absolutely, PV equals nRT would totally work. But I want to do it faster. So again, faster, 1.24, too many points, 1.24 liters of hydrogen. Wonderful, 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 nice, lovely. 1 mole of hydrogen is 22.4 liters. That's our little shortcut, only because it's at STP. And then we can just do our mole ratio, right? 2 moles hydrogen, which I erased my mole ratios, 2 moles hydrogen. Oh, I wrote it here. 2 moles water. Remember, hydrogen has to go on the bottom because we need to cancel out that unit. Now I'm at moles. Easy peasy, go to grams. 1 mole water, 18.02 grams of water. Now, again, we could have done this. You get the exact same answer, but this is just so much faster. Whichever one you want to do, it's fine. As long as I can see your setup, see your units, see your calculations, I don't care which one you do. Whichever one works better with your brain works for me. And again, you're going to get the same answer. So it just really depends on which one you like better. Okay, so let's try another one. All right, so I'm going to give you a couple minutes. Set this one up. See what you get. All right, so let's see. Try this one. Very similar questions than we did. Again, they're always a mix of stoichiometry, ideal gas law, or 22.4, but these are not at STP. So 22.4 is not an option. Okay, so try this one. I'm going to give you a couple minutes. If you're watching this now, do this now. If you're watching this later, don't just go, oh, I'm just going to eat my cereal or my food or my dinner or my pizza. No, don't do that. Try this, because when you do, Chem 101 takes a lot longer when you're not trying the problems in lecture, because you get stuck when you do these problems, but then I'm here to help walk you through them. So the next time you don't get stuck in the same place, you can go further and eventually you'll be able to solve the problem seamlessly. Okay, so try this one and we'll go over it in just a couple minutes. So might not have finished it, but got pretty close. All right, so what do we have here? So what volume of oxygen at 0.75 atmospheres and 313 is generated from the thermolysis of 10 grams of HGO? All right, so we're starting with, starting with this here, our HGO, and they're asking about oxygen. So again, this is our roadmap. So we're going to go from here to there. So there's going to be a mole ratio in between HGO and oxygen somewhere, right? So if the question is, we're starting with 10 grams of this, and we want to get here. Well, we can do that, 10 grams, molar mass, mole ratio, then we can get to oxygen. And then we'll be to our moles of our oxygen. And then can't use our nice handy 22.4, can't do that. So then we've got our moles of oxygen. We've got a pressure, we've got a temperature, we have an R, and we want volume. Very similar to one we just did. Okay, so first we have to do a little bit of stoichiometry first, and then we use our PV equals nRT. So here's our moles, and again, remember, don't round until the end. So we don't round until we get to the very end. Gave you the molar mass. I try to give you the molar masses now just because, well, everyone knows how to add up molar masses, right? So I try to make sure to give you those molar masses. Okay, and then our next part, I'm not sure why it's going backwards, oops, is we just plug it in. So for our volume, V equals nRT over P, and there we are, we get our 0.791 liters. All right, any questions on these? So the stoichiometry of gases, again, there's no real like, do this, then do this, then do that. No, there's going to be a mole ratio. Somewhere there's a mole ratio. You got to figure out what's the mole ratio between. What are you converting to when? And then when are you going to do the mole ratio? Sometimes you have to get to moles first and then use PV equals nRT. Sometimes you have to use PV equals nRT to get to moles, right? The hardest problems are when you have to do PV equals nRT and a mole ratio and another PV equals nRT, which yes, that happens. And you're going to see variations on this in Chem 101. And again, we never really ask the same thing twice. They're always a little bit different. So as long as you're checking to make sure your units match, checking to make sure your units match, making sure you know which mole ratio you're using, you should be fine. Because again, nothing is new here. Stoichiometry, you did it in your last chemistry class, and we did it at the beginning of the semester. And then we've been doing gases, which you kind of did in your last class, and we've been doing for the last couple of weeks. We just put the two of them together. So it's just combining two things you already know into one problem. Okay. Now we're going to talk about quickly the difference between ideal gases and real gases. So we've been doing the assumption that gases are ideal. Now, remember from kinetic molecular theory, and again, you need to make sure you read in your book about kinetic molecular theory because we don't have time to talk in detail crazy about it. But in general, ideal gases, according to kinetic molecular theory, they have no attractions to each other. They expand to fill their container. They have perfectly elastic collisions, right? All these things are true. Well, I mean, not really, not necessarily. So we're going to look a little bit of the difference between ideal gases and real gases. So real gases often don't behave like ideal gases, especially at high pressure and low temperatures. And so we're going to talk about why. So again, big assumptions in our kinetic molecular theory that gases aren't attracted to each other and they don't take up space, right? But they do take up space and they are attracted to each other. So at low temperatures, specifically low temperatures and specifically high pressures, these assumptions are not valid. Now, the molar volume, remember, that's what we just did in our last lab. We figured out the molar volume at an ideal gas's molar volume at STP, right? That's what molar volume is at STP is 22.4 liters. Well, at STP, pretty darn close. They're all pretty darn close to 22.4 liters, right? But once we get away from ideal, things change. Okay, so now we're going to look at, here's our molar volume, right? Just again, that's what we did in lab, the volume in 20 at STP, 1 liter. And here's our pressure. So as you can see, at low pressures, again, this is atmosphere. So we're at like 1 atmosphere, very low. But these are very, very high pressures. So you can see, so our ideal gas is the one that's the red. And then we're just going to use argon because it's easy to use in this one. So at low pressures, yeah, they really, you can't even tell the difference at low pressures. But the higher the pressure we get, the more the gas deviates from what an ideal gas is. It's because when the pressure is higher, those molecules are hitting the sides of the container much, much, much harder with much, much, much more force. And so they're actually taking up space. So the volume of a real gas is larger than predicted at high pressures. So they don't behave ideally at high pressures, very high pressures, by the way. Okay. Now let's look at the effect of volume. So again, at high pressures, the amount of space occupied by the molecules is a large piece of the volume. The molecular volume makes the real volume larger than what we would expect according to ideal gas laws. And so I think Jonas van der Waals, that was his name, figured out how to calculate, how to account for this difference in the volume. And we call this the van der Waals constant. And this one, there's a few of these. And this is we're going to talk about our van der Waals equation. And so he modified the ideal gas, PV equals nRT, to account for molecular volume. And I'm going to show it to you in just a second. So B, which is his, so B, we call it the van der Waals constant, and it is different for every size of the gas, for every gas, because they're all different sizes. So it's like PV equals nRT, but you can see here, plus NB. This accounts for the moles of different gases, and it's just, B is just a constant, right? So it's just a constant different for every gas. And again, this is because the particle size makes the volume greater than expected at high pressures. Okay, so again, now the other one is temperature. So at low temperature, so here's temperature, low temperature, high temperature, low pressure, high pressure. Up here at high temperature, almost exactly, real gases and ideal gases, pretty much identical. But when we get down here to lower temperatures, not so exact, right? Because molecules at lower temperatures actually attract each other, right? When gas molecules are moving super fast by each other, if this one's slightly negative or this one's slightly positive, or right, if they're both nonpolar, they're intermolecular forces, right? They're moving so fast, they don't have time, right? They don't attract. But if they're moving slower, they have time to attract. And so there's actually attractions. So at lower temperatures, because of intermolecular forces, the collisions will actually matter and decrease the pressure. So it decreases the number or the force and the number of collisions of the molecules hitting the side of the container, because instead of being perfectly elastic, they're like, oh, hi, right? And then they actually have these attractions to each other. And so it's these intermolecular forces that have the pressure lower, see how this is a lower pressure than the ideal gas law would predict. So at low temperatures, intermolecular forces actually makes the pressure lower than we would predict. And so van der Waals figured out a constant for this. So he said at low temperature, the attraction between the molecules is significant. There are intermolecular forces at lower temperatures. And so they make the real pressure less than ideal gas law says. And so he figured out another constant to actually account for this attraction. And here it is, A. So when we combine all these together, we get a very not fun equation to do. And so here is the ideal gas law, but combining and adding in intermolecular forces and particle size. So this is the van der Waals equation. And so you can see it's still the ideal gas law. So PV equals nRT, but we're accounting for our new constants due to both of our intermolecular forces and our size. And for each gas, this has already been accounted for. So like, for example, the identity of the gas is important. So helium, here's your A, helium, here's your B. That doesn't point to B, that points to N, and et cetera. And so for each gas has actually been done for us. So let's try one of these. So these problems aren't like particularly difficult. The math on them is just super annoying. And that's what makes these difficult. So you do them and do them the exact same way you've done all your other equations. You just have to go and look at a table to find the values of A and B. Okay. Okay, so let's practice this. So here is our equation. It's kind of a fun one, or our question. So patients suffering from chronic lung disease often rely on portable oxygen tanks or compressed oxygen when they're out and about. The tanks have a volume of 2.24 liters and a mass of 0.5 kilograms when filled to typically contain the recommended pressure. What is the pressure at our temperature 20 degrees Celsius, and we want pressure? Calculate your answer using both the ideal gas and van der Waals. So from here, this is our kilograms. From our kilograms, we can get to moles. So we do PV equals nRT. We have a volume. We have a moles. We want pressure. We've got a temperature and we have R. So PV equals nRT, nah, not a problem. Van der Waals, okay. So calculating this using PV equals nRT is not going to be hard for us, but the van der Waals, kind of a lot. So what we have to do for van der Waals is we have to look at the table. So if we went back to this table, we go here because we're talking about oxygen, right? So I'm just taking those numbers from the table and I'm just putting them right here for you. Those are the numbers from the table, okay? And so when we do this, again, the intermolecular forces, okay, so we have to take into account for our intermolecular forces, and we have to take into account the actual volume taken up by oxygen. Okay, so when we do our kilograms, 0.5 kilograms, right? And by the way, yes, you still need to know this. A lot of times people are like, oh, metric conversions. Yeah, always. You have to know these metric conversions, right? And so we have 32-ish grams of oxygen in 1 mole of oxygen, right? And so we get what? 15, I just calculated this, 2.62 moles of oxygen. So that's how many moles of oxygen are in our PV equals nRT. I'm going to solve this using ideal gas laws. So again, we've got our volume, we've got our moles, we have our R, we have our T, plus 273. I don't know, whatever that, it's like what, 293. And then we just solve, right? So divide by V, P equals nRT over V. And we solve. We just plug it in and solve, right? I think I just have that for you on the next page. I do, because we know how to do this now. Very good. Here's our N, our R, our T over our V. And we get 168 atmospheres. So if this was an ideal gas, so if oxygen was an ideal gas, right? The pressure in an oxygen tank, those portable oxygen tanks, which we see, would be 168 atmospheres. But again, that's making some super serious assumptions. It's saying that there's no interaction, and yeah, they take up practically no space. But we find out that's not true. So we use van der Waals to figure out what the actual or closer to the real and actual pressure is. So van der Waals, which is kind of annoying, right? So van der Waals equation again, remember, PV equals nRT. So if we rearrange it, which, let me go back to your whole van der Waals. So here's the whole van der Waals equation. I'm going to adjust this because we want pressure. So I'm going to solve this for pressure. Right, so I'm going to solve this for pressure. So all I did was rearrange this, okay? So if you solve this for pressure, you end up nRT over V minus NV. So those of you who are like, what did you do? Oh, I just did a bunch of algebra. Again, the most annoying part of van der Waals is the algebra. It's the rearranging of the equations. Some people don't like to rearrange the equation. Totally fine. I like to rearrange the equation. You can just leave it like this. Put in all your numbers. Hold on. Put in all your numbers and then wait for here and then distribute it all out. You can absolutely do it that way. How you do your math, it's totally up to you. But I just rearranged the equation. And then we just plug it all in. So it was 15.62 moles, right? 15.62 moles times our R, 0.08206. I'm not going to put in my units, okay? Times our temperature was 293. And then over, our volume was 2.24 liters minus our moles again. And so whenever you see N, that's your moles every single time. And then I don't remember what B is. Hold on, I gotta go back. B, 0.0318 times 0.0318. And I'm sure there's units there, but I'm not gonna write them down. Minus A, I forgot A, 1.36. 1.36 times moles again, 15.62 moles over our volume. And our volume is 2.24 squared. Yeah, so these numbers here, B and A, B and A, are always going to come from a table. Yeah, so here's our B, 0.0318, here's our A, just straight from a table. So again, this is the only new thing here is we're putting in an A and a B, and then the algebra is just kind of awful. So, but it is just algebra, which, I mean, I hate algebra. So those of you who hate it, and then we're literally, yeah, exactly what Carolyn just said. We're just plugging it in. Oops. Then you plug all this in your calculator and pray you did it correctly. Right? That's pretty much what we're doing. So the math here is much harder than the chemistry. Okay, so when you do all this, which I'm pretty sure I solved all this on the next page, I'm not putting this into my calculator right now. I did, I put it all right here. Oh yeah, I couldn't get this on one, when I typed it, I couldn't get this. So this is like minus that whole box right here. It's exactly what I wrote here. So what was that? It was 200, this is 215.4. Ends up being atmospheres minus 661. 661 atmospheres. Well, I think I wrote that wrong, 66.1. So that equals 149 atmospheres. So you can see the true pressure is not the same as the ideal pressure. I'll come right back to here. Just I want to remind you. So we calculated that our pressure was 168 atmospheres using ideal gas law. looking at our true, 149, right? So our pressure was actually less than we would predict according to ideal gas law, and quite a bit differently, right? Because we're at a lower temperature. And so we would expect that it would indeed be less. Okay, so let me go back to the one where I solve it all nicely. And again, this box here is this right here. I just couldn't get it all in one. All right, so when using van der Waals, the A and the B come from the table. Depends on the identity of the gas. So you just look up the identity of the gas and you plug it in. The algebra is the part that's hard, this one. Okay, any questions on this? And so again, van der Waals just takes into account the size and intermolecular forces in the equation, where ideal gas law says everything's the same and there's no interaction, which isn't really true. All right, any questions on van der Waals? Okay, so this is the end of our gases section. So this is what your homework is on for this week, is on gases. And your quiz next week is also on gases. So this is what your quiz is on next week also. Believe it or not, we are getting kind of close to your exam again. So now we're going to start on solutions. So we're going to start it today, finish it Tuesday, and then Thursday won't be anything. We won't be doing this material anymore. And then your exam is the next Tuesday, like another exam. Okay.